method that is introduced in this computergram lobster to extract chemical bonds from electronic structure data. So, does this work for you?
Yeah.
Okay, very good. So I will now continue without asking more questions. So when you do electronic structure theory and arrive at some result, and I give you two examples from recent research from my group. It's completely unimportant from which papers these result. You usually end up with a plot, say, energy against volume. For example, in this particular case, here we were doing many years ago total energy studies on tantalum oxide nitride. And you can see that there are three polymorphs and they differ in volume, they differ in energy. And this would be the typical result of an electronic structure theory calculation. But you do not know from this plot why this particular polymorph is less stable than, say, this particular polymorph. And you do not know the reason why there is such a large volume difference. This is another paper of ours. This was on the first helium compound, sodium to helium. And then you get some electronic structure data, say, from the density or density differences. And this is nicely colorful. But nonetheless, there is no understanding in such plots. So the total energy or densities or energy versus volume, even the density of states is insufficient for understanding. And let me quote a former advisor of mine. This is Roald Hoffmann, when he was celebrating his 80th birthday a couple of years ago. So he wrote quite a while ago, half a century ago, a very interesting statement. And I read this to you. To understand an observable means being able to predict, albeit qualitatively, the result that a perfectly reliable calculation would yield for that observable. Now, all of us are calculating all the time. We're using supercomputers and we're running plenty of calculations, but we would like to get rid of calculations. You know, if you understand the result, if you understand the calculation, then you do no longer have to calculate, because you can get rid of calculations and predict things as a human being. So this is what real understanding is like. And the question is, how have chemists approach chemical understanding of chemical bonding? So I usually start with this chemical bonding triangle, according to Van Arkel and Ketelaar. And now we plot the energy electronegativity difference against the mean electronegativity. And you immediately realize that there are three kinds of chemical bonding: the ionic case, the covalent case, and the metallic case. Of course, you find the ionic materials here, metallic ones here, and typical molecules over there. So how about chemical bonding in this particular case? So to begin with, ionic bonding is trivial, because if an electron hops from atom to another atom, it is in a one-center expansion of this particular atom, and then you have just electrostatic forces. And this is the reason why you find ionic bonding in standard solid-state chemistry textbooks already from the 1930s and 40s and 50s. So this is basically trivial. It is far more difficult, non-trivial, to deal with these kinds of interactions, namely the quantum chemical one, the covalent one. And you had to go into the year 1927. So 1 year after Schrödinger's equation was constructed, and then Heitler and London started with the first approximation of the hydrogen molecule. So this is really quantum chemical. If you want to do with covalency, you might need quantum chemistry. In addition to this, there is also a metallic bonding, but this is relatively simple. It's a special case of B. So if you have too many atoms and too few electrons, This particular kind of covalency is called metallicity, metallic bonding. So how do we do with this chemical bonding here? And as said before, this has been carried out in 1927 already within valence bond theory. It's more or less an outdated theory. Nowadays, we do it with molecular orbital theory. In molecular orbital theory, we approximate the molecular orbital as a linear superposition of two atomic orbitals for the case of hydrogen-2. And without specifying the Hamiltonian, you can directly show what the result will be. You will have a molecular orbital that is lower in energy, and here's the molecular orbital mathematically expressed as a plus-plus combination of the 1s atom, 1s atomic orbital on the left and the 1s atomic orbital on the right. And of course, there's another one, the anti-bonding combination, where you have plus-minus combination. So this is constructive interference, and this is deconstructive interference. And this is also scaled by the overlap integral. So let this be 0.5, then it would be 2 times 1.5. So you have the square root of 3, and here it would be 2 times 0.5, which is 1. This would be the square root of 1. This is the reason why this molecular orbital is higher in energy, and why also the coefficients are larger. And this also is, you can also look at this from the energy. So the energy goes down, in this case, and the energy goes up. So it's very simple. And if you deal with any other molecule, like in the H2 case, you can arrive at a good quantum chemical description of whatever molecule. This also satisfies the exchange, interelectronic exchange, but there's no correlation so far. So that would be the Hartree-Fock limit. If you release this electron, and this also can go into the excited state, you go towards configuration interaction, taking care of correlation. But basically, this is solved. Now, how about the solid state? For the solid state, as you probably know, you have to deal with infinity, because a solid state material is infinite in all 3 dimensions. And this problem was solved by Felix Bloch many years before he did nuclear magnetic resonance theory. So I'm reading this quote from him. It's originally in German. This translation is, I've done this one into English. When I started thinking about the problem, I realized that the main difficulty was to explain how the electrons could pass all the ions in the metal undisturbed. So he's dealing with metals in the late 1920s. To my delight, I found by a simple Fourier analysis that the wave differed from the plane wave of a free electron only by a periodic modulation. And here it is. This is the periodic modulation. And according to Bloch, we just have the solution of Schrödinger's equation at some particular point, and it depends on the wave vector k, which is introduced to get rid of infinity. And then we can write down the wave function at a different translation vector. That's all. Very simple, but extremely fundamental for solid state physics. And you can also show a picture that represents this formula, and this I'm showing to you on the next slide. So for a one-dimensional chain of hydrogen atoms, which is the simplest crystal you can think of, only hydrogen atoms on only one-dimensional. So we only have translation going to this direction. For the gamma point, then this periodic modulation will be just 1. So it's the 1s function, another 1s function, and another 1s function, and so forth. At the boundary of reciprocal space, you will have a plus-minus sign. So it's plus, minus, plus, minus, plus, and so forth. And because of this, you can immediately draw by hand the band structure of the simplest crystal you can think of, a one-dimensional chain of hydrogen atoms. And that's how it looks like. So for interatomic spacing of 3 angstrom, you can hardly see the dispersion. But when the atoms getting closer together, the dispersion will strongly grow. So for 1 angstrom distance between the atoms, you have this very strong dispersion. So this is the simplest one. You can do this by hand. And if you can do this in 1 dimension, you can also do this in 2 and 3 dimension. And it is done routinely throughout the world, everywhere, also at your place. And you know this very well. So if you want to say calculate the band structure of diamond, we can directly draw the bands, calculate it using Bloch's theorem, and we can k-space integrate, average this to yield a density of states. That is also a standard tool in solid state theory. Now, this was done using density function theory because we have to at least approximately take care of the interaction of all the electrons. And this is routinely done, whether you use a plane wave program such as VASP, or you use quantum espresso, or you need UpInit, or any other method, it will give you essentially the same result. There's only one problem, namely, what about chemical bonding? And despite the fact that you sometimes see papers in which people discuss chemical bonding based on density of states, you will probably realize that no information about chemical bonding is contained in the density of states, because the density of states does not contain the phase information. So it does not contain whether an interaction between atomic orbitals is in phase or out of phase. So plus minus signs is not given by this. So how have the chemists been doing with chemical bonding? Now we've seen the molecular orbital diagram of H2 already, and it was Mulliken many years ago in the 50s, 1955, that he came up with the first population analysis. So what he did, he took this particular molecular orbital and squared integrated this. And it must be 1 because it's an atomic molecular orbital, I'm sorry. And if you square integrate this according to the molecular orbital linear combination of atomic orbitals approach, this will have a left part centered on the left hydrogen atom, a right part centered on the right atom, and an in-between part. This is so-called overlap population. Now, this is, of course, 1 square integrated because it's the atomic orbital, and we just have the mixing coefficients for the molecular orbital. C1 for the left atom, C2 for the right atom, and the in-between one. Now, if you have atomic orbitals, you can do this. And you can do this for any kind of molecule. You can also do it for the solid state material if you use a computer program that uses atomic orbitals. But the workhorses of nowadays electronic structure theory, such as VASP, quantum espresso, or UpInit, they cannot do this. Why? Because they are lacking atomic orbitals. They don't use atomic orbitals, they use plane waves. And this is a big problem. This is the reason why still many people are unable to extract the chemical bonding information from their plane wave data. So let me illustrate this to you with another example. So instead of having a one-dimensional chain of hydrogen atoms, I now take a one-dimensional chain of sodium atoms. And I'm depicting here a wave function at X, so at the zone boundary for sodium 3s atomic orbitals. So this wave function will look like this. It starts here, then it has many wiggles, then it goes down, has more wiggles here, and it goes up with many wiggles here and goes down. So here, the wave function is telling us I'm a 3s sodium atomic orbital. And here the wave function is also telling us I'm a sodium 3s atomic orbital, but I have a negative sign because this is a wave function at the zone boundary. And it goes back to a positive sign, and it goes back to a negative sign. In between, it looks like a sine or cosine function. So that's a plane wave. So a real wave function contains this atomic orbital-like part and a plane wave part. So how did the scientists get rid of these wiggles? So they get rid of these wiggles because of an ingenious invention by Hans Hellmann in the year 1935. I'm asking the younger people among you to look up this paper in Journal Chemical Physics, the year 1935, volume 3, page 61. It's a one-page paper. And he's dealing with the idea that an electron approaches a sodium cation. And this 3s electron will not fall into the nucleus, but it will be repelled by the already filled inner core shells. So the 2s are filled, the 2p are filled, and the 1s. Because of this, we just have a weak pseudopotential. And for the cesium atom, this pseudopotential will be even weaker because there are more electrons filled already. So if we replace the real potential of the atom by this pseudopotential, what you do, you incorporate the idea of the periodic table into quantum mechanics. That is the idea, because all the atoms in the same group of the periodic table have similar pseudopotentials. So this is an ingenious idea by Hans Hellmann in the year 1935. And if you do this, you get rid of the wiggles and you just have sine and cosine functions. And then you also have accurate Hellmann-Feynman forces. And this idea is useful up to the present day. Of course, we have different pseudopotential. Right now, these are PAW pseudopotential, but the idea is the same. I just want to remind you, you probably haven't heard about the history of Hans Hellmann. He was born in Germany, started studying physics and electrical engineering, then changed to chemistry and was willing to write his habilitation thesis in quantum chemistry in the year 1933. But then he was kicked out of Germany. He had to emigrate to the Soviet Union because his wife was Jewish. So in the year 1933, when the National Socialists had come to power in Germany, he had to leave Germany. So this is the last picture taken from him with his mother and his sister. So he went to the Soviet Union, to Moscow. He became a professor at the famous Karpov Institute in Moscow, and he wrote the world's first quantum chemistry textbook, first in Russian and then in German. I have a personal copy from the year 1937. However, there's also a new version of this, freshly typeset in German, and there's also a new version of this one in Russian. So if you are able to read Russian or German, I strongly recommend this book. It's a wonderful book because he's telling a lot about quantum chemistry in the year 1937. However, in the year after, he was accused of being a German spy, which he wasn't. And he was killed, murdered actually, by Stalin and his comrades. So since the time, most people don't know about him. And sometimes it's getting forgotten that he invented pseudopotential theory. So let's use a second to remind also about the accomplishments of Hans Hellmann. So pseudopotentials, we just have this plane wave. And the wiggles are gone. So it is wonderful for electronic structure theory. This is the reason why these codes are so effective right now, but because there are no atomic orbitals left, you cannot do population analysis. You cannot extract chemical bonding unless you use Lobster. So what does Lobster do? Lobster reads your pseudopotential PAW output, whether it's from VAS, quantum espresso, up in it, has no importance. And then it has several sets of atomic orbital bases, the best you can get. And it used this later type orbitals to do a projection. What it does, it makes a unitary transformation between a completely delocalized representation, which you use using plane waves, into a completely localized representation. And this is done opposed to the Vanya method, which is done in real space. This is done analytically and accurately in reciprocal space. And then you have a representation of your extended electronic structure with the atomic orbitals. And then you can do all kinds of chemical bonding analysis. So let me show this to you. You have seen the band structure of diamond. You see the density of states already. And this is what the crystal orbital Hamilton population analysis looks like. So this contains the phase information. And all the bonding states go to the right and the anti-bonding states go to the left. So the valence bond is entirely carbon-carbon bonding, whereas the conduction band is entirely carbon-carbon interbonding. This was done, really 30 years ago, but with a different code. Lobster was not available at the time. This is also another thing done 20 years ago without lobster. You probably know that the crystal structure of tellurium, which has this strange helical structural component. So you see it's like a chain of tellurium atoms, where every tellurium atom is bonded to two tellurium atoms. And you can easily see the similarity to the simple cubic, the polonium structure, which is the higher homologue. And it turns out when you use a lot of pressure, you can press tellurium into the simple cubic structure, and then it becomes a metal, and it is strongly tellurium-tellurium interbonding. This is the reason why you need at least 15 gigapascals to force it into the structure. And if you release the pressure, you will have a band gap, and the interbonding states will be strongly reduced. So this is a three-dimensional Peierls instability suggested by Rudolf Peierls also in the 50s, and you can immediately show this through a chemical bonding analysis. This is something that could only be done with lobster. You'll say you study the chemical bonding in the carbon nanotube. Now so easily done using plane waves, fast, up in it, quantum espresso, whatever. And then lobster reads this data and immediately projects out the sigma contribution between the carbon atoms, which would be dubbed sp2 in valence bond language, with a very, very small interbonding signal here, because it's not flat, it's curved. And the pi bonding is somewhat higher, as expected from quantum chemistry. And there's also very small interbonding peak here. So this is as expected from quantum chemistry of carbon molecules, but now done for a carbon nanotube. This is a typical solid state case. You probably know the crystal structure of scandium telluride. So this is from the third main group. So it is trivalent scandium 3+. And this is from the sixth group. So it's tellurium 2-. So this is electron precise. This fulfills the octet rule. Scandium 3+ has a noble gas shell, and tellurium 2- has also noble gas shell. This is the density of states. And then it doesn't surprise you that the entire valence band is bonding. And then only the conduction band becomes interbonding, just like diamond. It's different for antimony 2 tellurium 3 because this is from main group 5. So if this is trivalent, and it is trivalent, it still has 2 more electrons, 2 additional electrons. This material is in conflict with the 8-n rule. And you can see this because these are the 2 leftover electrons, which you usually would call lone pair electrons. But they are not alone. They show up as anti-bonding levels in the upper part of the valence band. It's very typical. Now, this is an old example, but I'm showing this for purpose. This was also done 20 years ago, more than 20 years ago. Do you know why iron is a ferromagnetic material? In order to find out, we calculate iron without magnetism. So without spin polarization in the body-centered cubic structure. And these are the bands. So this is the 4s band, which continues here. And then you have 1, 2, 3, 4, 5 3D bands. This is the 3-peak shape density of states. This is all 3D, only this is iron 4s. And then you see that the levels are all bonding with the exception of an anti-bonding level at the Fermi level. And this calls for yet another Peierls distortion. Geometrical distortion, but there is no geometrical distortion in iron. What happens in iron? Iron spin polarizes. So, and when it's spin polarized, the alpha spins in this density of states go down. The beta spins, the minority spins go up. This is known from solid state physics textbooks. Now, this is quantum chemistry. The bonding that goes back to the majority electrons goes down. the bonding that goes back to the minority electrons goes up. And because of this, you get rid of this anti-bonding level and you strengthen the iron-iron bonding by 5%. So for iron becoming ferromagnetic, it is due, from the chemical perspective, it is due to a stronger bonding in the spin polarized case. So there's a new option in lobster introduced in the year 2020. Now we can also color the bands. So imagine you would run a calculation on thallium fluoride. So this is from the third main group. But it is thallium 1+, because it's also F-. So also the thallium contains 2 additional electrons, lone pair electrons. And now we plot the bands. So these are exactly the same bands, but we plot them according to the bonding or anti-bonding character. So here we concentrate on the interaction between the thallium 6s and the fluorine 2p orbitals. And you can see that the upper part of the valence band is anti-bonding. However, an interaction between the thallium 6p and the fluorine 2p is bonding. So you can immediately trace down, even from the band structure, the amount of chemical bonding originating from different atomic orbitals. Let me say a few words about atomic charges. Sometimes you need to have atomic charges for a good discussion, for a comparison with the experiment. And there are basically 2 approaches in the literature. Well, the one nowadays quite popular is due to Richard Bader. He concentrated on the electron density. Bader hated wave functions and atomic orbitals. The other one, which is clearly more elegant, if you have the wave function available, is to calculate the charge directly from the wave function or from the orbitals, as introduced through Mulliken and introduced through Löfting. Now, why is Bader so popular? Because up to now, with the exception of lobster, nobody knew how to exactly project down to atoms in plane waves. So if you're using plane waves, you usually use the density, because in the plane wave calculation, the local density of states do not add up to the total density of states. But the density is fine, so therefore they chop the density. This can be done. There's a good algorithm, but sometimes it fails. And I will show you one example. This is an example carried out by a former coworker of mine, Volker Deringer, one of the best students I ever had. He's now become a professor at Oxford. So he was calculating battery material, carbon 216, an amorphous carbon backbone into which lithium was inserted. And when you calculate the beta charges, which takes an awful lot of time, you find that most lithiums are positively charged. But there's one lithium atom which is negatively charged. And this is pure nonsense. This is chemically as well as physically impossible, because carbon is far more electronegative than lithium. This is just nonsense, despite the fact that it has been calculated according to the Beta principle. Usually these complete failures do not get published, but fortunately Deringer published this. So people see how bad a beta charge analysis can really become. The algorithm is faulty. Or you can do this from the wave function using lobster, and then you find that all the lithiums are cations, are positive, or close to zero, in harmony with nuclear magnetic resonance. So this is far better than doing this with beta. Why did people use beta? Because they did not know how to project to atomic orbitals. This is the reason why they went through the density. There is another very interesting result about the charge calculation, say from a Mulliken population analysis. If you do this with regular molecules, this you find in standard chemistry textbooks, that there is some basis set dependency in molecules. Say you plot the Mulliken charge of the hydrogen atom in methane, ammonia, water, and hydrogen fluoride. And of course, they differ from each other because in hydrogen fluoride, the hydrogen atom will be more strongly charged than in methane, for example. But as a function of the quality of the atomic orbital basis set, there's some basis set dependency. But this is no longer the case in plane waves, because plane waves are not local, they are delocalized. And then when you do a straightforward plane wave calculation and then generate the charges either through Mulliken or Luftin automatically using lobster, you might find very nice results, which are also far more efficient than beta. So imagine you calculate electronic structure of this material or that material, awfully complicated materials, or such an intermetallic material, strontium, aluminum, germanium. So this would be the amount of time for VASP. This hardly to see red thin line is the amount lobster takes to calculate the charges. And this is the time beta needs to calculate the charges. You save 1 order of magnitude. And the same for this material, and also the same for this material. This material is so large that the beta charge calculation is still unfinished after so many core hours. So I highly recommend to you to calculate atomic charges directly from the wave function through lobster, mostly Luftin, but also Mulliken. It is far more accurate than beta and is far more efficient than beta because you operate with the wave function. So when you do this directly from the wave function, you can say for barium titanate, you find accurate charges for titanium, for barium, for oxygen. And you can also come up with automatic modeling energies that are based on accurate charges. I don't want to go into the details, but modeling energies have been very important in the past, in particular in solid state chemistry. This is everything done automatically. Now, there's some new development in lobster available since a few months, and I want to come to this in particular. It's the so-called crystal orbital bond index, something entirely new. The bond index was introduced by Wieberg and also improved by Istvan Meyer, who died last year, a famous Hungarian quantum chemist. So let's think about this nitrogen molecule, N2. So we have the two lone pairs here. We have the sigma bond and we have 2 pi bonds. Remember, nitrogen 2 has a triple bond. So this is the projected density of states from lobster. So you see the 2s, 2spz contribution. This is the crystal orbital overlap population projected through lobster as envisioned by Roth-Hoffman. This is the 1 sigma G molecular orbital, the 2 1p orbitals. These are the overlap population. This is the projected crystal orbital Hamilton population. So the sigma bonds, they lower this molecule by 14.4 electron volts. This pi bond lowers the molecular energy by 10 electron volts. And this is the crystal orbital bond index. And this gives you directly the bond order. The bond order for this sigma bond is exactly 1.0. And the bond order for this pi bond is 2.0. This is incredibly useful for complicated structures if you want to directly calculate the bond order, routinely done using lobster. There is another molecule I would like to show you, a molecule probably is known to you, a molecule that does not comply with the octet rule. It is in conflict with the octet rule, but it's known for a long time. Xenon difluoride. It's a 10 electron species. So this is a noble gas, xenon, and it's attached to 2 fluorine atoms. This is a stable molecule. You can also make a stable solid state material. Now, this is the crystal orbital bond index. And for direct interaction, so between xenon and fluorine, or between fluorine and fluorine. So let's look at fluorine xenon, xenon fluorine. You can see by the molecular orbital that you have a bonding xenon fluorine interaction because they have the same orbital phase. This is what you find here. Can you see this? And at highest energy, you can see that the xenon-fluorine interaction is anti-bonding, and this you can see here. You can also see that there is an attractive interaction between the fluorines, and this you can see here, between this fluorine atomic orbital and this fluorine atomic orbital. This is the reason why you find this over here. And this will be anti-bonding between here and here. It's a different sign, and therefore it goes to here. But since this is a 10 electron species, you not only find 2 center interactions, you also find 3 center interactions. So, and this is shown here in red, a 3 center interaction. And this 3 center interaction is bonding because this is bonding here and this is bonding here. A 3 center interaction. Also here, 3 center interaction and an anti-bonding 3 center interaction here. This is anti-bonding, this is anti-bonding as well. So this you can immediately and automatically calculate using Lobster: 2 center, 3 center, 4 center, 5 center, 6 center interactions, and so forth. Of course, it's becoming, you need more and more CPU time, but it's automatically done. And to summarize this for a moment, I just want to show you that you can, by the crystal orbital bond index, you can immediately characterize this bond. This is a single bond in diameter between the carbon atoms. In quartz, they have a 3/4 bond between silicon and oxygen plus ionic charges. And in rock salt, you have almost non-existent covalent bond between sodium chlorine, but strong atomic charges, automatically done. Now, finally, I want to show you something, a very fresh result that just got published in Angewandte Chemie, and this deals with phase change material, which are so important these days. So you probably know the principle of phase change materials used in DVDs and Blu-ray discs, and germanium telluride is a prototype. So this material is either crystalline in a metastable rock salt structure or amorphous. And by writing zeros and ones and reading them through a laser, you operate a DVD, a rewritable DVD, a rewritable Blu-ray disc. So this is the crystal structure. It looks almost rock salt-like, almost cubic-like. In fact, it is rhombohedral, hexagonal crystal structure. Now, this is not the only material, germanium telluride, in the distorted crystal, rock salt crystal structure, but you can also use antimony telluride to come up with the phase change material. And sp2O3 has this van der Waals gaps between different sheets. Then you can make solid solutions between germanium telluride and antimony telluride. For example, germanium sp2 tellurium 4, or germanium 2 sp2 tellurium 5, or germanium 3 sp2 tellurium 6. And this is the valence electron count that goes down from 5.6 to 5. And you see these are different stacking variants, mixes, solid state mixes between rock salt-like germanium telluride and rock salt-like antimony telluride. Now, these materials, as said before, are used in DVDs. They have extraordinarily large optical dielectric constant. They have an unusually large electric conductivity. They have a very large Grüneisen parameter. You have multiple emission events in atom probe tomography, and this van der Waals gap is too small by 12%. What is the chemical bonding in this material? So colleagues of mine dubbed the term metavalency from solid state physics because they think that these materials are between metallic bonding and covalent bonding. This is not incorrect, but it is there's a better description for this particular kind of material, which I'm going to show to you now. So we look into germanium telluride, and we look at different kinds of chemical bonding. Of course, first look at 2 center bonds, but this is trivial. And now we look at 3 center bonds, a bonding between tellurium atoms that are mediated through germanium. So it's tellurium, germanium, tellurium interaction. Just think about xenon difluoride, which I've shown to you. Fluorine, xenon, fluorine. Here it is, tellurium, germanium, tellurium. And you can see that there is a px-px interaction mediated by px. There's also an s-px interaction mediated by px. So there is indeed a 3-center bonding. It's a multi-center bonding in germanium telluride. And if you look at this, if you look at the interaction between germaniums mediated by tellurium, you do have a contribution mediated by px, but you also have, so between px and px, but you also have interaction between s and px, and they cancel each other. So the tellurium atom that has a noble gas shell does not mediate this bonding, but germanium 2 plus with the 4s2 configuration, with the 2 lone pair electrons, they are responsible for multi-center bonding. This is the interesting thing. It is just like in electron-rich molecules such as xenon difluoride. And this also explains why this van der Waals gap is too small, because there's a covalent bond. There's not only a van der Waals bond, but there's a covalent bond, a 3-center bond and a 4-center bond automatically detected using Lobster. So these are projected force constants, which are larger than you usually find them, particularly this one here, but also the blue one. And then you find 3-center bonds and also 4-center bonds that go beyond the van der Waals gap. This is what lets this van der Waals gap shrink by about 12%. So we find this very interesting. And we do not only find this in antimony telluride, but in all other materials that have a van der Waals gap. So please remember, metavalent bonding is known from the molecular case. Metavalent bonding is multi-center bonding, but not for molecules, but for solid-state materials. Solid-state materials that have too many electrons, that violate the 8-n, the octet rule. So if you're interested, please look into Angewandte Chemie. This has just appeared, and this is the cover picture of Angewandte Chemie. And this is the take-home message for today. Metavalency in phase change material is just multi-center bonding in electron-rich solids, not molecules. The phenomenon is known for decades already, but there was no tool to detect it in solid-state material. And since Lobster is there, Lobster can automatically detect it because it attracts 3-center, 4-center, 5-center bonds, and so forth. So let me summarize. Even when running extended plane wave DFT calculation, you can extract a lot more from the wave function besides the total energy. Of course, you want to have the total energy density of states, but you can extract more that is used to understand the material. Lobster reads these plane wave electronic structures and does a unitary transformation from the non-local to a local representation. And then you have all the tools available like a molecular quantum chemist. So these chemical bond information such as COHP, accurate density of energy, I didn't talk about this, fat bands, they can all be automatically done. And then you explain things like Pyatt's instabilities, ferromagnetism, and so forth. If you directly work with the wave function, not with the density, with beta, you have atomic charges that are both more accurate and far faster to achieve, at least 10 times faster. Now there's a new tool, the crystal orbital bond index, that helps you detect 3 of multi-center interactions, and this is all automatically done. And as I said before, the real important take-home message is that metavalency is multi-center bonding for electron-rich solids. Before I close, I want to show you where I'm right now. I'm in Aachen. Aachen is the most western town of Germany. So if you go from China, you can't go more for a longer distance if you go to Germany. So we're close to the border to Belgium, Netherlands. So this is the most important building at Aachen, the Aachen Cathedral, which is part of the world's cultural heritage. This is how people thought that Karl der Große, who united Europe more than 1,200 years ago, how he probably looked like. So finally, let me thank you once again for giving me the opportunity. I hope I didn't go over time. So this is about 45 minutes. again, thank you very much, and I would be happy to answer questions.
Okay, very excellent talk. And do anyone have any questions?
Dear professor, so very nice talk. So I have a question. In your talk, there is one slide regarding the magnetism in iron. In iron, so you use COHP to interpret that. So in my mind, there is another way.
Wait! I didn't understand. Sorry, I didn't understand it. Can you please re-say this? What did I do?
Sure. So in your slide, so there is one slide about the magnetism of iron.
Yeah, okay.
Yeah. So
I will show it to you.
Yeah, thank you. So typically it is very interesting because before your talk, in my mind, so my understanding is that so the magnetism is based on Stoner criteria. So
yeah, sure.
Yeah. So can you please comment on that? So
of course.
For them, thank you.
Yeah, of course. So I know this explanation in terms of Stoner's theory. First, there was Heisenberg's theory, which you cannot apply to itinerant metals because they are delocalized. And then there was Stoner's theory in the 1930s already. And the first accurate calculations were performed in the 1970s, 1980s. And since that time, for very good reason, the physicists argue in terms of Stoner's criteria. So you have exchange parameter and you have the density of states at the Fermi level, which you multiply, and then they should be larger than 1. Okay? And this is known for a long time. And we wrote a review in Angewandte Chemie in the year 2000. You may want to look it up. Year 2000, volume 39, page 1560. And we also commented on Stoner's theory, which is a fine theory for physics. But our problem was to make new ferromagnets and also antiferromagnets. And with Stoner's theory, there is no recipe to make new materials. It is a physics theory, and it cannot be applied to chemistry if you go into the laboratory. So we try to come up with an alternative explanation, which is chemical in character. So if you want to move from physics, say exchange parameter, density of states, to a chemical interpretation, you have to deal with atoms and bonds. And this is the reason why I come up with this. These are equivalent, but this is the chemical picture. And because of this, we have been able in the coming years to come up with dozens of new ferromagnets and also antiferromagnets. For antiferromagnets such as chromium, the Fermi level directly hits the non-bonding levels. So this is a different phenomenon. So you can, with this theory, you can cover both ferromagnets as well as antiferromagnets.
Okay, thank you very much. So then another question. So for example, is it possible to use the chemical bonding? So for example, Lobster COHP technique to understand in insulator, sometimes the material is ferromagnetic, and in other cases it is anti-ferromagnetic. So
yes.
So the competition between the two magnetic order cases.
Yeah, sure. Yeah. This has been done before in the quantum chemistry literature, not in the quantum physics literature. Yes, this has been done.
Okay, thank you. So I will take a look at that. Thank you.
Yeah, it is a matter of the electron count. Let me go back one slide. So this is the typical case for a ferromagnet. The Fermi level hits the anti-bonding levels. For an antiferromagnet, it is here. The Fermi level hits the non-bonding levels. And you can see this from the periodic table. For example, in manganese, you have a tendency towards antiferromagnetism. For chromium, you clearly have antiferromagnetism. Let me do this here. So here. And then you go to iron, which is ferromagnetic. Then you go to cobalt, which is still ferromagnetic. Then you go to nickel, which is still ferromagnetic. And then you move to copper, which is no longer magnetic. So it is a matter of the valence electron count. And there are some certain alloys where you can, through replacement of different metal atoms that provide different number of electrons, you can manipulate the Fermi level to make antiferromagnets and ferromagnets on purpose.
Okay, thank you. Very interesting insight. Thank you very much.
Thank you very much.
Anyone have any question?
Hello, Richard.
Okay.
Can you hear me?
Yes.
Hello. Okay.
Hello.
So, sorry, I was late, so I missed most part of your presentation. So, I got maybe a naive question. So, I want to understand, what's the correlation between the COHP are calculated between two atoms and to the actual molecular orbital bonding, like the bonding and anti-bonding states for this kind of atom pairs?
Well, it's basically the same thing. I will show this to you. Whoops. Yeah, here we go. So this is a very simple example for nitrogen molecule, N2. And do yourself a favor and write down the molecular orbits. Draw them by hand. You'll find them in any quantum chemistry textbooks. And then you can, exactly, I think we also give it in this paper. And then you can see in the crystal orbital overlap population, the crystal Hamilton population, you can see those levels. This is sigma bonding level. This is the pi bonding level. Then there's another little sigma level, which hardly contributes to chemical bonding. And when you integrate this with the crystal orbital bond index, this gives you 1, and this gives you 2. So this gives you the bond order. This gives you the energy contribution in the band structure energy. And this gives you the overlap. Usually nowadays people concentrate on COHP because DFT optimizes the energy. We're always arguing in terms of energy, right? And therefore it is useful to use COHP because it's about energy. Sometimes if things become very, very complicated, you also argue in terms of bond orders. And this is automatically done.
Okay, thank you.
Thank you.
Any other question from audience? Okay, Richard, I have a question.
Yes.
And I think in the very previous slide you showed sodium helium, and I'm asking what is the chemical bonding between the helium and sodium?
Oh, it's very simple. It's very simple. It is. We did this in the paper. So sodium to helium is very different. I don't have a slide here, but I can do it. But I can tell you. So when you squeeze sodium to helium, the pressure becomes so large that you squeeze out the electrons out of sodium. So you have sodium plus. And these two electrons, they go into empty sites. So you have a crystal that is contained of sodium cations, isolated electrons, which act as anions, and the helium atom is just a spacer. The helium atom prevents that the electrons fall back into the cations. That's it. So you have a salt. Sodium to helium is just like sodium chloride or magnesium oxide. But there is no anion. These are just the electrons that act as an ion. So therefore, you have a very large Madlung field. And we also showed this through a COHP calculation in that paper, which appeared in Nature Chemistry, I think in 2017 or so. So if you look into the paper, and particularly the supplementary material, we show a COHP plot, and then you immediately find that there is no sodium-helium bonding, there's no helium-helium bonding, there's no sodium-sodium bonding, but there's bonding between the sodium and the electrons, but over a distance, and the distance is kept by the helium atom. It's a salt.
Okay. Thank you. I understand. Okay. And any questions from the audience? Okay. I think if no questions, we can close this talk. And we are pleased to invite Richard and thanks him to very excellent talk. Okay, thank you.
Thank you very much.
Thank you very much. Okay.
Like, say goodbye, right?
Goodbye.
Thank you.
Bye.
Thank you. Bye bye.
Bye.
Bye bye.
Bye bye.
Bye.